Hello, in this video I'm going to go through the first section of the Oxford PAT, the physics assessment test from 2006. I'm not doing the whole video, the whole paper in this video. I'm going to split it across multiple just so I don't end up with this massive hour-and-a-half video. So if you want to keep going after this first section, then look out for subsequent videos. In this one, because they change it year by year, often you can use a calculator. G is taken as 10 meters per second squared. Let's see how we get on with these multiple choice ones. So question 1, in the equation x equals ut plus a half at squared, the term ut represents what? So we've got a velocity multiplied by a time, so that's going to leave us with a displacement. That's our accumulation of the velocity is the displacement. Question 2, block of niobium metal with that density and sides of, right, so those are the dimensions of the block. What is the maximum pressure that can be exerted by this block when it stood upright on one of its faces? So we're going to want to stand it on the smallest possible face, because we've got pressure is force over area. So in this case, the force is the weight. So we want to have the weight over the area. So our maximum pressure is going to be the weight divided by the minimum area. Our weight is going to be equal to the density times the volume, which gives us the mass, multiplied by G. We're going to see here, so our volume is 3 times 4 times 5, but our minimum area is going to be 3 times 4. So they are going to cancel when we divide out. All we're left with then is the density 8570 multiplied by G, which is 10, multiplied by the one dimension that hasn't been cancelled, which is this 5 centimeters, so 0.05. Let's get rid of a few zeros, so that, and that can all go away. So we're left with 5 times 857, or half of 8,570, which is 4,285 pascals, which is, no, it's too big for B, so there we go, A. That wasn't too bad. Diagram below shows the approximate orbit of the dwarf planet Eris around the Sun. Eris, I don't know, whichever way. Which of the following statements is false? So we want one false, so we'll go through all of them and hopefully only one of them will end up being false. Does it move fastest at point D? So at point D, we've got maximum GPE because it's furthest away from the Sun. So we must have minimum kinetic energy. So that already looks false. So let's circle that as our answer. We could also have this with, what is it, Kepler's second law, that is sweeping out equal areas. So if it's further away, it needs to be moving a shorter distance to sweep out the same area, if you compare it to there. So yeah, it has to move further here than it does at D. So different ways of thinking about that one. For B, does it move at the same speed at points A and C? A, C look more or less the same distance away, so same GPE, so same kinetic energy, that seems fine. Does it move in an ellipse with the Sun at one focus? Yep, that's Kepler's laws again. Potential energy changes during the orbit. Yes, we've got interplay between potential energy and kinetic energy, as you know, well, that's life really, isn't it? So sticking with A. Question 4, hollow toy boat floating on a bath. If you take a teaspoonful of water out of the bath, put it in the boat, what happens to the water level in the bath? So we're going to have Archimedes' principle in play here. When we remove the water, so that's fine. So you remove it, take the teaspoonful out, and the water level will drop by a teaspoonful. Now we're going to put that teaspoonful that we've taken out, we'll put it onto the boat. Now we're going to get, it's going to float. So we need, from Archimedes' principle, the buoyancy is going to be weight versus weight. So we're going to need to displace a volume of water that has the same weight as the teaspoonful of water, which of course is going to be a teaspoonful of water. So it will go back up by a teaspoonful. So it's gone down by a teaspoonful and up by a teaspoonful. So we end up in the same place, which is C. Question 5. In quantum mechanics, the Broglie wavelength of an object depends on its momentum according to this equation, where h is the Planck constant. Protons of charge E, mass m, accelerated from rest through a potential v. What is their de Broglie wavelength? Right, so yeah, we've got the lambda is h over p, so that is h over mv, which means we need to do h over the square root of, well, if we take half mv squared, that's the velocity that we're going to be getting for this proton once it's been accelerated. If we multiply that by 2m, then we've got m squared v squared at the bottom, so we can just square root it. It's a sort of standard trick of flicking around between kinetic energy and momentum. So we'll do that. The what have we got? We've got the charge E, so the energy that is going to have this is the kinetic energy is going to be, potential is joules per coulomb multiplied by coulomb, so that's going to be EV. Well, that should be a multiplied in there, that's what I said, but I wrote down a plus for some reason. Then we need to multiply by 2m. So all in all, we've got that it is Planck constant divided by the square root of 2mev, which hopefully is one of these. Yeah, that is B. Okay, so yeah, that's fine. But yeah, this trick of, I suppose there's different ways you can do it. But if you need to get from that half mv squared to a momentum, then it's kind of the obvious way to do it, really. You know, multiply by the 2m and then square root everything. Right, anyway, moving on to question 6. A car accelerates steadily from 0 to 20 meters per second in a distance d and time t. Another car takes a time 2t to accelerate steadily from stationary to the same final velocity. What distance does the second car cover during the new acceleration? So distance covered is average velocity multiplied by time. They've both got the same average velocity of 10. So this one's just taking twice as long. So it's going to go twice as far. So D. That's a really quick one. Right, alien civilization is in the business of building custom solar systems. Their basic model has 5 planets in circular orbits at distances d that are perfect square multiples of a basic length. So, okay, 1, 4, 9, 16, 25. Yep, the model, for this model, the year lengths of the planets are in those ratios. How are D and Y related? So if we're saying that D is going to be, well, we've got A, because it's going to have some multiple in there, A to 4A to 9A to 16A to 25A. That's what's going on with D. We can say a similar thing, let's say with B's for years, 27, 64 and 125 B. So we need to get from D to Y. So we need to divide by A, then we need to square root, then we need to cube, and then we need to multiply by B. So they're the 4 steps that we need to do if we're going to get from one of these, whichever one we pick, to the other one. So Y is going to be equal to, we're just putting all this in order, so D divided by A, square rooted, then cubed, and then multiplied by B. Okay, so let's just take these constants into one place, because I see in the answers that we've only got K's everywhere. So we've got all the constants just grouped together, which is fine. So that is going to end up being B divided by A to the 3 over 2, so A root A, multiplied by D to the 3 over 2, so D root D. So we can just call this B over A root A, just some other constant, because A's and B's are constants, that's fine. So we need a D root D in it, that looks like C. Right, there might be quicker ways of doing those. I'm not sure. I find with those that I like that very step-by-step logical approach on it of putting the A's in. I mean, I know really you don't need to put in these A's and B's. I just find it settles the question down somewhat, that you can really break it down into these steps here and then worry about the constants later on. So, but yeah, other methods are available, I suppose, as they are with all of these questions, really. Question 8. A Martian attempts to measure his mass using a set of bathroom scales in his house on Mars, gets a reading of 93 kilograms. Unfortunately, his scales were designed for use on Venus. Given that the gravitational strengths of these on the 2 planets, what is his true mass? So if he's on Mars using Venus scales, is expecting a force divided by the gravitational strength on Venus. That's what it's expecting. It's expecting to use this 8.8. So we're on Mars where it's actually 3.8, but it's using this 8.8. So we've got some weight, which of course we need to divide by this. You can tell with the units, we're getting a reading of 93 kilograms. So that is the weight divided by this 8.8 newtons per kilogram, because then when we do that, the newtons on the weight, they cancel and we end up with kilograms. So we've got this going on, but we don't want to divide by 8.8. We actually want to divide by 3.8. So we're going to need to multiply by 8.8 and divide by 3.8 in order to get the actual number. So the calculation we want to do is 93 multiplied by 8.8 divided by 3.8. That's what we need to do. So I'll just pop that one into the calculator. Well, it's 93 times 44 divided by 19. So yeah, okay, I'm just going to put that in the calculator. I mean, what is that anyway? That's about 2 1/3, that one there, that fraction. So it's going to come out at C, but let's type it in anyway. 93 times 44 over 19. Yeah, it comes out at 215. Yeah. So yeah, I think sometimes people, they know they need to do something with these, but it's seeing what is it expecting, what are the scales expecting to be using, and that's going to be the gravitational field strength for what they're for the planet that they're designed for. So thinking it through that way. All right, question 9. I think there's only 2 more to go in this. When a metal bar is cooled, it contracts. Which of the following is true? Its density and mass increases. Well, no, the mass bit isn't going to change. Density increases and the mass remains constant. Well, that sounds good because the volume's gone down, so the density will go up. So let's put that in tentatively for now. Density and mass are unchanged. No, because the density is definitely going to change. Mass remains constant. The density decreases. No, so that would have to get bigger. So that's wrong as well. So yeah, we'll stick with B on that one. Yep, last one. Hot air balloon is descending at a steady speed of 11 meters per second. Pilot drops a sandbag, takes 7 seconds to fall to the ground. What is the height of the balloon when the sandbag was released? So the accumulation of the acceleration in 7 seconds is 70 meters per second, because we're going to get 7 times 10. So that's our acceleration. So we've got a final velocity of 11 plus 70 equals 81 meters per second. So we need to do that. The distance is the average velocity multiplied by the time, which is going to be, average velocity is 92 over 2 multiplied by 7. So that's going to come out at, which one is it going to be? It's going to be this one. It's going to be C, because it's got to be just less than 350, give or take, isn't it? Because you've got, if you did 750s, you get 350, and then we've got to take off 28. So yeah, 322. So yeah, they were a pretty straightforward bunch of 10, relatively speaking. None of them are easy, particularly in exam circumstances, but You know, maybe because it was the first year, the first batch of multiple choice questions weren't as bad as some of the ones they've had in later years. You know, don't take that to mean that, well, you should be getting all of these first try, otherwise you're hopeless. But they're, hopefully you'll be able to see if you did get one wrong, it was just an easily corrected misunderstanding. So if you want to keep going on these, I'll put section B in the next video.